All right, we should probably start. And I'm sorry, I'm a little bit disorganized this morning. Alarm clock didn't go off, and I had to get kid to school late, and things were just chaos. So hopefully, things will go smoothly. But I wanted to start by asking how things are going with this exercise that's due today. Good, bad. How many people feel like they're having major problems? At least a few. Yeah, yeah. Okay. Um, so again, like we've done for the last couple weeks now, we will have time after we finish with some introductory stuff to work on the exercises, and Jorgen and I are both here to help with questions about this exercise number 9, and the fact that you're having problems with it still is not a huge surprise, but it is a good segue to talking about the course feedback stuff. So I posted in Slack asking for feedback again. I unfortunately didn't get a chance to look one last time at the responses before getting started this morning, but there were a few rather obvious general themes. One of them being that a large portion of you are of the opinion that the course is too difficult, too much work, and you're considering whether or not to continue doing the amount of work needed for the course. So that kind of speaks to a few things from my perspective. One is, well, it's not our intention to have the course be something that requires 30 hours a week of work outside of the classroom. Obviously, if you're taking other courses, that doesn't leave a whole lot of time for them. So I'll say for sure that this week's exercise should be much more straightforward. It's a bit unfortunate that with introducing pandas stuff this year, a few of the exercises that were relatively simple, or at least much less challenging last year, became more challenging when having to deal with pandas. Some of that might be the fact that I don't really know what I'm doing with pandas, and I'm just trying to adapt to the fact that you guys learned that in the lecture, so I feel like I should try to allow you to continue using pandas rather than forcing you down the route of using NumPy. But yeah, there's, this exercise this week, I think you'll find to be much more clear and much more obvious. And in fact, the focus is really on only doing a couple things in Python and thinking a little bit more about geology for this exercise. So that should hopefully also be good for the majority of you. Another thing that I wanted to say just about the feedback is beyond the number of hours that are being put into the exercises, there are a number of people that are feeling like they don't really know what they're doing on top of that. So you're kind of like copying and pasting things from last week's exercise because it worked, but you don't really know always what that code did or fully understand kind of how things are working. So again, I think in this respect, at least, the exercise for this week should be a little bit more obvious. You have to do a lot less Python coding, and the things you have to do, there's really just kind of one or two skills that I'm hoping you can focus on for the exercise for this week. So in some sense, I'm hoping that this will be a little bit of a review, so that you can go back and kind of practice some of the things you've already learned a little bit and maybe build some confidence so that you're not feeling as overwhelmed. With that said, I guess my plea to you is just to sort of be patient and see how things go this week before you throw in the towel and say, I can't do this anymore. The other thing I have to just note is I don't know, some of you might be aware, this is the first time that I'm teaching the course as a required course for the bachelor students. So previously, in years past, I was only getting students that were wanting to learn Python, not people who were maybe a little bit apprehensive about learning Python, and that's also something for me that I'm needing to kind of think about as an instructor, because some of the exercises were more challenging deliberately in the past, because some of the average skill level maybe of the students was a bit higher, and that some of them had past programming experience, or some had already even done things in Python, and so I'm trying to kind of find a good level. The whole point of teaching the course, and the reason why we made it a course that's required for the bachelor students, is that I want you to learn a little bit of Python, and I want you to feel like you can use it. And if that doesn't happen, then the course doesn't really serve its purpose. So again, that's why I asked for the feedback, and why I'm going to try and sort of continue to tweak the exercises a little bit for the rest of the course, so that things don't continue to get more and more difficult. But I think you'll see that this week and maybe the next few weeks will be a little bit more closer to the level where I think they should be. So are there any questions, or does anybody have anything about the course feedback? I'll take another look at it, and if there's any other points that are big things, I'll try to make note of them. But on average, I think the average sort of rating for how demanding is the course on a scale of 1 to 10 was 7.5. That's not terrible, but that is a mix of bachelor's and master's students, so it may be that different people have different views. But the number of hours per week was pretty high on average. I think it was over 20 hours, or maybe not quite 20 hours, but it was a lot. So that's the part that concerns me more than the challenge of the course, is just the time it's taking too. Yeah, so that's that. And I think what we can do now is move to our focus for this week. And this week we're going to talk about more or less focusing on an equation rather than kind of statistical stuff. We're going to focus on this diffusion equation, and if you're a little bit worried about that, don't worry too much. It's not going to be kind of heavily into the derivation of the diffusion equation and how to solve it. There is some material on that, but that's not the focus. The point is that the diffusion equation is probably the most commonly used equation in the natural sciences. So it's a good thing that you should have some sense of what it is and some geological applications. So we're going to start actually with a short lecture on the diffusion equation and how it's applied, with some examples from geosciences. And then after that, I'll just show you that there are some notes on how to solve the diffusion equation that you'll probably want to take a look at those for the exercise, but you don't need to necessarily do the solution yourself. And then, as usual, we'll preview the exercise. There's one other thing, though, that I wanted to mention about, I think some of you have been asking about this final course paper thing, kind of wondering what that's all about. I had hoped to, again, have a little bit of information for that today, but maybe on Wednesday I'll bring something to the work session, just a little bit of information about the course paper. I can also put something in Slack, but I think what it ends up being is that the past years we've taken exercises 13 and 14, where you basically produce a whole bunch of plots. You don't really have to do a ton of Python coding, but you produce a bunch of plots for changing different values in a simple Python code. And then the exercise was basically to take some of those plots and write up like a short scientific article. I think it was, last year it was 8 pages in length. Years past it had been 6 pages, and I think this year I might actually move it back to 6 from 8 pages, because moving it to 8 pages I hoped would make things better last year with the quality of the papers, and it didn't help. So there's no point to make you write 2 more pages if it doesn't make anything any better. I might also say, like 6 to 8 pages if you want. If you feel there's something you really want to say, you'll have the opportunity. But basically, you'll have these plots, and I give you a couple scientific articles to look at, and then you write up a paper where you kind of describe the scientific problem, show some of your results, and I think it's, once you've done the exercise, it's not really too difficult, especially because for the exercise, all you really do is have to make some plots. You don't have a lot of time, like writing Python code and other things. The exercise in years past has taken not that much time. So, yeah, the problem is that I can't really give you too much of a head start on the paper because you don't know the material from the last 2 weeks, which is really what the what the paper is based on. So I could give you the articles and things like that in advance, but it might not make any sense until we get to the last 2 weeks. So anyway, I'll put some things together for Wednesday so that at least you can get some information. And I'm only able to be here from 9 till 10 on Wednesday, so I can maybe say something about it, but I can leave maybe some little printout thing with Yorina so that if anybody comes after that, she can give you the kind of overview of what the paper should be about. So that's that stuff, and yeah, we're going to move here. As I mentioned, we have a kind of short lecture thing on diffusion and the diffusion equation. The idea for what we're going to do is first just introduce the process of diffusion. Probably you're already familiar with this, maybe not so much how it's applied in geosciences, but in terms of physical phenomena, diffusion is something that we're all aware of, whether or not you know the name. And then I'll show a little bit of the math for how the diffusion equation works and kind of break that down just so that you can understand where the different terms in the diffusion equation come from and what they mean. And then I'll show some examples from geomorphology of hill slope diffusion. And I guess, has anybody had a course in geomorphology before? One? Yeah, maybe. So I'm not assuming necessarily that you know that much, but that at least you'll see some pictures and you can kind of relate what's happening to those pictures. So as I mentioned, the goal here is to introduce diffusion as a process, and then to show some examples of different diffusion processes that happen on hill slopes. So on the areas next to or beside rivers, and so there's some examples of the processes here, and we'll see what those are. Just as a general process in terms of geosciences, diffusion's pretty common in many different ways. So at the crystal scale, when you have deformation of crystalline materials, one of the ways in which the sort of atomic scale deformation takes place, essentially at the larger scale acts like a diffusion type of process. So the random changes in the crystal lattice end up giving you an overall sort of diffusion process that can be applied then to understand how rocks deform. There's things like the process that I won't get into much detail about it in the lecture, but there's some extra slides at the end if you're curious about rain splash. So when raindrops hit the side of some sloping surface, they tend to spill more sediment downslope than goes upslope, and essentially because of this dependence of the slope of the surface where the rain strikes, it acts like a diffusion process that ends up moving material more quickly downhill where the slopes are steeper. And another example is from thermal chronology. which again is probably not something that's that familiar to you, but when you have things like helium or argon, these noble gases that are trapped within a crystal, they don't go into the crystal lattice, but they just get trapped within the structure, and they can diffuse out of the crystal as a function of temperature. So as it gets hotter, it's easier for the gas to diffuse toward the edge of the crystal. So there might be some concentration of gas within the crystal, and then at the outside the concentration is zero, and that tends to cause material or the gas to move towards the edges of the crystal. So there's at least a few examples there. I could come up with a handful of others, but these are just some that are familiar. As a process, again, you probably already have some familiarity with diffusion, but it's a process that results in mass transport or mixing as a result of random motion of diffusing particles. And that's probably easiest to see in a picture. So if you have two different materials, one made of atoms of A and the other made of atoms of B, whatever these things are, doesn't really matter. But initially they're separated by some barrier, which is this red line here. You see over here on the left side this plot with the concentration of A. And so here the concentration of A is high, and on the right side it's 0. Yeah? And I guess you can all imagine what's going to happen when we take the barrier away. It's if we have a random movement of the particles within this, so if it's a crystal lattice structure or just atoms inside a gas, they start to mix with one another, and gradually what ends up happening is the concentration of A starts to decrease as atoms of B migrate into the zone where previously there was material of A. And likewise, as the atoms of A move to the right, basically what you see is a mixing of the two materials. And you can see, of course, that at first, the gradient or the change in concentration between A and B is very steep, and gradually it gets shallower through time. I guess this concept is somewhat familiar from chemistry or other courses. I mean, you could do this, this could be the same picture of something that's hot and something that's cold, because heat conduction is basically a diffusion process. You could think about, I guess I usually give some kind of silly example of, someone wearing an excessive amount of cologne who comes into a room, and gradually, like you can see, the ring of people that get offended by the smell gets bigger with time as the sort of particles of the cologne mix in the air and spread. So however you want to think about the diffusion process, this is the basic idea. And again, it's a very common process in many different things. Just want to point out here, I'm going to use the term concentration gradient sometimes, and that basically just refers to the slope of this line here. So what you can see initially is that's almost a vertical slope, so very high concentration gradient, and then through time that slope gets shallower and shallower. So the gradient in the concentration of A and B decreases because you start to mix in some of the atoms of B where you had only A before, and vice versa. So we won't worry about this other thing for the moment. But I guess that's the picture, and that should be hopefully somewhat clear. Again, the definition up here. And what you tend to see is whether it's heat or whether it's mass, is you see material that moves from where the concentration is high to areas where the concentration is low. It is happening just by random motion, but you could imagine that when you have one place where you have a very high concentration and you just start randomly interchanging particles, that you're going to have material moving from the area where the concentration is high. And the general idea with diffusion is that it reduces gradients in concentration. So initially, we had A and B separated with a very steep gradient, and through time they start to mix, and the concentration gradient goes down. So, yeah, that's the kind of general picture. Now, there is a more quantitative definition, right? This is a quantitative geology course. So, we could put things in slightly more mathematical terms. I personally don't find this to be any more obvious. I think the other definition, although it's qualitative, is easier to understand. But we could say that diffusion occurs when a conservative property moves through space at a rate proportional to a gradient. Now that probably doesn't mean, it means very little to me, and maybe means quite little to you at the moment. But a conservative property is just something that is a property that should be conserved in a system. So if it's heat, then we conserve energy when heat is conducted. So the kind of general governing physical law is conservation of energy. If it's mixing of two gases, we conserve mass, or mixing of two materials in a crystal lattice. We assume that we're not creating any mass or losing any mass, but we're just have mass that's changing places in the crystal structure.
Can it be related to the system achieving equilibrium?
Yeah. Essentially there is a steady state that it will eventually be reached. Now, if it's, if you take an example of two gases mixing, of course the steady state is where the concentration gradient is 0. But yeah, there is you can kind of calculate timescales for that kind of thing. Yeah. So we have to have something that's conserved in the system. Diffusion doesn't work if you're adding mass or removing mass, and that's fine. And then the rate of change being proportional to the gradient, that will make a little bit more sense probably in a few slides. But essentially, the idea is that the movement or the sort of changing of particles from either side of the system, if it's A and B, occurs in relation to the change in the gradient in the concentration. So here's just an example of a hot piece of metal that's put in contact with a piece of metal that is cold. Initially, the gradient is very, very high, and the place where the change in temperature occurs most quickly will be at that, or right near that interface. So, you'll see far away, if these are two metal bars, far away at the ends of the bar, it takes a long time for the temperature change to be felt, so to speak, whereas right at the interface, the temperature change is very rapid. And that has to do with the gradient in temperature being very high at that location. So what I want to do now, and oops, I guess this box didn't cover that fully, the text. But what I want to do is take a look at basically breaking down this definition a little bit into things that we can understand more easily just as sort of geoscientists. So we had the general definition here where there's two parts, this conservative property, and then there's this rate proportional to a gradient. So for the second part, essentially what we can say is the transportation rate, or the rate of heat conduction, or whatever, is proportional to the change in concentration over some distance. And that's essentially just rephrasing this in slightly more comfortable terms. Again, if you think about the two bars, the change in concentration over some distance initially will be very large over a short distance, and over time it gets bigger. The distance does. So this transportation rate essentially is, you could also call that a flux. Maybe it's not that familiar of a term, but if you have some rate of transportation of some material, if you have some rate of conduction of heat out of the surface of the earth, you can call that a flux. This is proportional, doesn't change. And then we can say this change in concentration over some distance, we could just again call this concentration gradient, as we did before. The whole point of this is that if we convert this to sort of more mathematical terminology, we can basically convert this to an equation pretty easily. And symbolically, we can then say that the flux, it could be just replaced by the letter Q. This little alpha is the proportional to symbol. I don't know why it's so small. And then we have this delta C over delta x, which is just the change in concentration over some horizontal distance x. So this, I think maybe you have some picture in your head at this point of what this means. But this is one component of the diffusion equation almost exactly. We would have to replace this proportional with some other kind of constant. But essentially we have a flux that's proportional to the change in concentration over some horizontal distance. So this could be the change in temperature over some distance or whatever. If it's a concentration of atoms A and B, then this is a mass flux. So does that make sense? Sort of. Or is this completely like, I see a few people in the front nodding, but they're, for those of you in the back, is this kind of idea, I guess the physical picture makes sense, yeah? What about the mathematical part? Are you comfortable with this sort of level of math? Yeah, there will be some sort of integral and differential terms later, but those aren't as really important. It's just understanding this relationship between the flux and the change in concentration along some distance. Okay, so here, again, we have our little picture of the atoms of A and B. If we want to convert this to an equation, it can be solved over any spatial scale and solved with integral calculus. You can basically take this Q is proportional to delta C over delta X thing and replace these deltas. These are just finite differences. So that would be the concentration at this point versus the concentration at this point. And replace those with the difference over some infinitesimal distance. And so, that's, if you've done anything with calculus, that's always the kind of way in which things go. You take the limit as this distance goes to 0. So we're just going to say, for our purposes, it could be just some extremely small difference in concentration over some extremely small distance. And so then in that, we also put in this d here. So now we have Q equals minus d times dc over dx. These two things are basically, the blue term is the same as it was before, but we're just considering it over some very small distance. And we replace this alpha, this proportionality thing, with being equal to minus d. So we put in some constant here called the diffusivity or diffusion coefficient. And so that's just going to scale this whole term in blue. And again, if you want, you can look at the example of the concentration of these atoms A and B. And what we see here is that the flux of atoms of A is equal to this diffusivity times dc of A divided by dx. So this is the change in concentration of atoms of A over some small distance here, x. That's one part of the diffusion equation. And I guess without belaboring it, this seems to be okay. Now, there's a good question here. Why is there a minus sign? And I think because I don't really want to make you suffer too much, I won't try to push you to answer that question right now. But what we could do is we could consider the concentration at two different points. So if we have some point here, x1, where concentration of A is C1, and another point over here, x2, and we have the concentration at that point is C2. Right? Again, this is the concentration of atoms of A, so it's basically 0 over on the right side, and 1 or whatever on the left side. Now, if we took that as a finite difference, we could just say that instead of having this dc, we could replace that with delta c, or c2 minus c1. So concentration here minus the concentration here. And over some distance, x2 minus x1. So what we see if we take c2 minus c1 here, doesn't matter what the actual number is, right? But it's going to be negative. Yeah? I guess you all see that? Yeah. And x2 minus x1 is going to be positive, so this term is negative. So negative number divided by a positive number is a negative number. And then we multiply that by this minus d. So negative number times a negative number is positive. And so what we see is our flux, without putting any numbers in, should be positive. The flux of A from this point to that point should be positive. And indeed that is what we end up seeing here, is that we see atoms of A moving to the right. So the flux of those being positive. The negative sign basically comes from the fact that this difference we have here is going to be a negative value multiplied by another negative to give you this flux of atoms of A to the right. So, you know, maybe that's there in a little bit more detail than you need. Maybe there's not quite enough detail, but essentially I tried to spell out the math pretty explicitly so that I'm hoping you're able to follow at least where that part of the equation comes from. And we can move to the other first bit that we said, this conservative property moving through space, which again is a little bit harder to translate. It's also a little bit more abstract. I guess the conservative property part, this, you know, whether it's mass conserved or energy, that maybe makes sense, but the moving through space is a little bit strange. But if we talk about it in terms of concentrations, we could say the change in concentration with time is equal to the change in transportation rate with distance. And so this, you know, whether it's conservation, mass, energy, whatever, this property that's being conserved is equal to the rate in which it changes with distance. Or the rate of change in concentration is equal to the flux gradient. And this is probably a little bit confusing what the flux gradient means. Maybe it will make more sense when we put the letters in there from the equation before. But we had Q in the first equation we looked at for the flux, right? Q was equal to minus D times dc over dx. That was our flux. Now we're talking about the gradient in flux. So if we had concentration, we saw that concentration gradient was how the concentration changes. Flux gradient is how the flux changes. And again, if we put it in terms of mathematical sort of symbolic representation, we see that the change in concentration, delta C, everybody's okay with that one, divided by delta T, so that's time. Okay, nothing scary there, so just change in concentration with time is equal to minus the change in flux over some distance, delta x. There's nothing here in terms of letters that should be too scary. Now, I don't necessarily think that you should go, oh, okay, I totally get it. I could, you know, draw the plot of this equation. That's not the point right now. It's just to say that this thing's not that scary. So that's the, you know, the kind of general relationship we have when we translate this first part into math. And what this is basically some kind of statement of conservation of mass or conservation of energy. We'll see how that works in just a second, but this is basically conservation of whatever equation. So the question is, yeah, well, how is this a conservation of mass or conservation of energy equation? Again, you could think about it in terms of the fluxes, right? This delta Q thing up here is simply Q2 minus Q1. Doesn't matter where you are. It's just the flux at some point minus the flux at another point, and the location would be x2 and x1. So if we have these different fluxes, I will maybe ask you this question, and that is what happens when the flux of mass at Q2 is larger than the flux of mass at Q1. So if you look at the equation, let's say we want to look at this change in concentration. How would the concentration change when Q2 is bigger than Q1? And again, you can assume the same thing that we have before, that position x2 is further from the origin than position x1. Yeah? So you'd have some, right? This Q2, if that's bigger than Q1, of course, the term up here is going to be positive. The x2 minus x1 should be positive, but there's the minus sign out here. So the concentration should go down. So if there's more mass that's moving away or taken away at some more distant point than some point closer by, we should expect that the concentration goes down. Again, you can look at this in the same representation that you can see with respect to this little animation here. We take the concentration of atoms of A, we replace these deltas with the little partial differential, so dc over dt. Same thing we had before, we've just put it into this sort of integral calculus form, equals minus dq over dx. And it says basically that the concentration of the atoms of A is going to change based on the flux across some point at x minus the flux at some other point x plus dx. So if we look here, I don't know if I don't have it in as separate points here, but if you consider some point here to the left of the red bar and some point over to the right of the red bar, the flux at those different points will be either positive or negative, and the change in flux will tell you how the concentration of A changes. Probably, I don't need to keep just talking about math. It's maybe better to move on and show you some examples, because you'll get a chance to play with the equation in the exercise. So as noted here, there's some notes in the lesson for this week. They're noted as optional, but there's a section called Solving the Diffusion Equation where you can kind of see how you can put those two equations together and then solve it for a simple example to see how the diffusion equation works. So we now have some idea in terms of the general mathematical representation. If you don't like math, maybe this is the painful part is over, and now we can talk about some geological processes. And to do that, we're going to talk about hill slope diffusion. And this is kind of a general name of just a group of geomorphic processes. So things that modify the shape of the Earth's surface, that operate in a diffusion-like manner. And you'll see what this means in just a moment. So first off, when we talk about erosion in different landscapes, we have to talk about the length scales that we're considering. And generally speaking, in geomorphology, we separate things between short-range and long-range processes. So if there's sediment being transported in a river that goes tens to hundreds of kilometers from its source, that's a long-range transport process. Material that's riding on top of a glacier might be transported also in sort of a similar way. So fluvial processes tend to be long-range. Things that happen on hill slopes, so something that happens between a ridge here and the valley, the sediment transport along this hill slope is a short-range process, and that's what we're going to focus on, is things that are happening just at the scale of hill slopes. So I guess the term hill slope, is that familiar enough? Yeah? Do you know what I'm talking about when I say hill slope? Yeah? Okay, because if you don't, it's not going to make much sense when we go into talking in detail about hill slope erosion. So we'll see some pictures, but basically, we're talking about anything that's operating in the areas between some ridge and a valley as hill slope processes. And so there's lots of examples of these different kinds of things. Some of them are probably more familiar than others, but we're talking about movements of mass on hill slopes like landslides, mudslides, anything, rock slides, some cohesive chunk of material that slides along some well-defined surface. That's a definition of a slide. Flows are things that are moving relatively quickly, but may not have some clear kind of detachment surface that's a well-defined thing. And then actually what we're going to focus on is this stuff down here at the bottom, which, it's called heave, or that's one of the kind of general terms for a group of different geomorphic processes. And these have to do with movements of material that have forces that move perpendicular to the Earth's surface. So a good example here would be like freeze and thaw weathering, where water is in some pore space, it freezes and the water expands, and when that expands it tends to move perpendicular to the Earth's surface, and then when it contracts, the sediment that was entrained there tends to fall close to vertically back down because it's being acted on by gravity, which wants to make things go straight down. You'll see some examples of that stuff. So this is like a little ternary diagram, I guess, for the geoscientists, right? You guys see these things for all kinds of different examples. I remember lots of them from petrology and mineralogy courses with different, you could put different feldspars on the corners if you want or whatever. Here we have one between slides, flows, and heave. Here's our focus in the little blue box. And so we're not talking about stuff that happens fast. So here we have like from slow to fast and from dry to wet. So rock slides happen fast and they're dry. Mud flows happen pretty fast, but they're obviously a lot wetter. We're talking about stuff down here. Seasonal soil creep, things that are almost too slow to monitor. So you might say, well, it's not really that interesting if it happens so slow, but well, that's your opinion. So when we talk about heave and creep, creep is basically this, again, the definition's not that clear. I think the pictures will help show it, but we have movement of material that's extremely slow and it's in response to gravity. Heave is this kind of vertical part of the system. So movement of materials related to expansion and contraction. So if this is freezing and thawing, if you have clay-rich soils or something like that, you can have swelling and contraction related to how much water's in the clay, or lots of other things like that. But this results in material moving down slope, even when there's not a very steep surface. And so soil creep is something that happens that we could probably see even here. We could probably find examples if we walked around on the hills around Kumpula. We could probably find examples of soil creep. Here's a nice picture from a location, I think somewhere in the eastern US, but I'm not certain about that. But hopefully you can see somewhat this almost vertical bedding in the shale down here. Can you see that? I know the picture doesn't look that good. Can you tell that bedding is vertical there? Yeah? And you can see obviously that the orientation of bedding changes quite a bit as you get closer to the surface. So this part of the material is being affected by seasonal creep, by sort of water getting in there, and expansion and contraction as it freezes and thaws, and that's causing this material to tilt and move downhill. And so, if you're a tree sitting on there, sometimes you'll see trees that get a bend in the trunk because they're riding along and they're trying to grow up, but the soil underneath them is moving, and so that happens. Anyway, that's kind of a nice photo. Here's some other examples of heave and creep. where, you know, this is probably the most common thing that you have perhaps seen, these kind of bent tree trunks on slopes. You know, that doesn't necessarily happen just because it's on a slope and the tree starts growing perpendicular to the slope, because the trees tend to grow up to begin with. But this is happening because the soil itself is moving downhill, and as it moves downhill, its orientation may change and cause the tree trunk to bend. There are other things, like if you have snow on here, you can also get sort of this snow pressure effect where the snow will also move downhill and can push on the tree trunk and cause it to bend. But that's, you know, this is just kind of a nice example that, again, you've probably seen just walking around in the woods. And, you know, here's another example of a sort of telephone or electricity pole that's been tilted over by the gradual effect of soil creeping downhill. How does it work? Well, basically what we have is two different phases. We have this kind of expansion phase and contraction phase. So expansion could be from swelling. If it's clays, it get moisture in them and expand, or freezing of water. And that expansion caused some particle here to move up, basically perpendicular to the Earth's surface. And then when things either thaw or when the water moisture level drops, you have this contraction phase, and that phase is basically one in which gravity causes the material to settle close to vertically. So in perfect unconsolidated material, this would fall straight down to the surface. What happens in reality is that it falls at some angle that's not quite vertical, but not along the same way in which it expanded to begin with. And you can see, I guess, pretty easily that if this happens and this particle goes up here and then goes down and then goes up here and goes down, it will move downhill. And it doesn't happen very quickly because freeze and thaw cycles aren't that rapid. But over years, and as sort of geoscientists, we don't have any problem to see that this will transport material significant distances over time. It's just not something you're going to sort of get your camera out and say, you know, I'm going to watch soil creep in action. At least not unless you've got a really long delay between when you take your pictures. So if you look at the picture here, what kind of things do you think might influence how quickly this soil creep or creep process happens? Amount of water, for an example, yep. Yeah, I think the mass could possibly have an effect. So we got water, we got the mass. What else might have an effect here? Yeah, right. I mean, you know, you've got to, like, how many freeze-thaw cycles you have. If it's, you know, constantly frozen, then soil creep doesn't work. There are other things that could happen, but there's one other one that's kind of important. Yeah. So the slope, the angle of the hill slope itself. You could imagine if you took an extreme example of a slope that's almost vertical. Now, I'll tell you that soil creep doesn't happen on those kind of hill slopes. But if you had one that's almost vertical, when you have this expansion, the material is going to move this way. And then when you have the contraction, it's going to go a very long way down the hill slope before it settles. So, and you could take the same example of a surface that's totally flat. It just expands up and goes straight down. Nothing actually moves. It just goes up and down. So if it's horizontal, you have no soil creep. If it's extremely steep, you don't have soil creep either. You have some other process, but it gets more efficient as the slope gets steeper. So I think we got most of them here. Particle size, composition, moisture, and slope angle. There's lots of things that go in here. But the thing that seems to be the strongest effect is this slope effect. And because the rate of transport depends on the slope, you can model this as a diffusion process. It's very much the same idea as depending on the concentration gradient. It depends on the hill slope angle, the hill slope gradient. So the mass of material is proportional to the topographic gradient, or the steepness of the slope, which means we can do this as diffusion. So that's the kind of introductory stuff, and here are some questions, and well, I think I will maybe just check in and see, how much of this lecture actually sunk in. So what are the two components of a diffusion process? We had two pieces. So what about the concentration of, so the conservation of mass? Yeah. So we have some part of this conservative property moving through space. So there's that part. What was the other part of the definition? What about the gradient? Does anybody remember? The slides are online already if you want to cheat. But, maybe you're already looking at them. So we've got this sort of part related to the conservative property moving through space. That includes a bit the time component there. The other part related to the gradient is the rate of the process being proportional to the change in gradient. If I'm not mistaken, we should have that thing right somewhere here. Conservative property moves through space at a rate proportional to the gradient. That's our general definition, and we'll get to explore that a little bit more coming up. How does it that the soil creep process works? We just went through this. So does anyone want to kind of explain what's the general way in which, this particles of whatever soil sediment move down slope? Yeah, right? So this sort of expansion that happens more or less perpendicular to the Earth's surface, and then the settling that ideally would be along some vertical trajectory toward the center of the Earth. And the main factors, well, we just talked about those a second ago, so we don't need to talk about that. But the hill slope is the big thing. The amount of water and the frequency of freeze-thaw cycles, of course, that stuff will affect things as well. But the rate is going to be strongly controlled by the hill slope angle, for instance, for soil creep. So what I will say here is that's our lectures more or less done. There are some other examples here if you're curious. I just put some extra slides in. These were in the lectures in the past, and so there are things that happen in glacial landscapes like solifluction that might be interesting to you if you're interested in glacial and paraglacial landscapes. There's a bit more on rain splash if you want to see how raindrops cause sediment to move down slope, or things like tree throw. So we had some good examples of tree throw from August of this past year when there was the big storm that happened and blew a bunch of trees down. When trees tip over and the clump of soil that's at the base of the tree gets pulled up, if it's on a slope, it tends to fling more of that sediment down slope than up slope, and that also is basically a diffusion process. And a nice other example is related to gophers, these little kind of squirrel-like creatures that live underground. And when they make holes, they, when they dig things out, tend to throw more sediment downslope than they throw upslope. And so gophers are also diffusive geomorphic agents. So there's a few more slides if you want. You could take a look at those if you're curious about other examples. And maybe it's just kind of interesting to know that people look at gophers and think, ooh, geomorphology. So with that, I'll just show you, if we go back here to the lecture, or the lesson, sorry, We have our lesson overview here. We've gone through the slides on diffusion. I guess if you click the link, yep, you get those slides. So you're free to look through those. There's some notes here about solving the diffusion equation, and I'll just point this out quickly, that this just goes through some of the equations we saw and solves them solves for the general case of the diffusion equation. This is used in this week's exercise. So the thing I want to show you is down here toward the bottom, there's this last equation in the section on solving the diffusion equation is this one here. This h of x equals this stuff. You don't need to know what these letters mean right now, but this is an equation you have to put into Python. So you're going to want to come find this guy and use that. In addition, there's some things down here at the bottom that you will also want to use because you're asked to display some values on your plots. And so without talking in detail about what these mean right now, I'll just tell you that you're going to want to look at the bottom of this page for the equation to use and for some values to put on your plots. You can feel free to follow through the other part of how do you get to this equation if you like, and how do you actually put together the diffusion equation, because we saw the two pieces, we didn't actually put them together into one equation. So that happens right here, and maybe that's of interest to you, maybe not, I don't know. But the notes are there if you want. So then for this exercise number 10, I'm just going to take a look here at the GitHub repository, and I was making some updates last night. Hopefully all this stuff is properly set up. But our exercise for this week is on hill slope diffusion. So some of the stuff we just saw in the lecture you can now play around with a little bit. And in this case, what we have is a broken Python script to plot the shape of a hill slope that's experiencing diffusion as its main geomorphic process. And so you've got to make some changes to the script, including putting in the equation for calculating the height of the hill slope to get the sort of shape of the profile. And then you've got some different numbers you can put into the script. Most of the stuff, if you look here at this Python script, you can see actually you have most of the script here. You're asked to put something in right here, which is the equation, and then you're asked to put in some calculated values that you can find in the notes on solving the diffusion equation. There's some stuff in there. Otherwise, you're going to play around with changing some of the numbers up here for the different parameters of this hill slope diffusion model. Now, it occurs to me that I do maybe need to draw you a picture in order to show kind of what this thing is meant to plot. My hope here is just to give you another opportunity to translate an equation from some written form into Python. That's the only thing I really want you to focus on in problem 1, and I hope that's what you're going to end up doing. There's a couple other things you'll have to pay attention to, but I hope that's the main focus. Then you're going to put some text on your plots using this plt.text. We're not doing anything with pandas date time indexes, so you don't have to do anything tricky. You just look at the coordinates on the plot where you want to put the text, and you put in those coordinates, and the text will show up at that location. So that should hopefully be good. In point 4 for the problem, you'll see that you change some of the parameters, and you just look at how your hill slope changes. And each time you do that, then you just save the plot, and that's that. So that's more or less what you do in problem 1. In problem 2, we're going to go to look at an example from the Sierra Nevada mountains in the western part of the U.S. So here is the state of California. The location that we're looking at is this little black box here in the western side of the Sierra Nevada. So here's the kind of relief or topographic map, and you can see there's some profile that we have here going across this thing called an interfluve. That's just what separates the two rivers. And so we have a topographic profile coming across here, and that thing is basically looks like this. So the river's down here, here's the elevation of the surface, and then there's another river on the other side. The idea with this part of the exercise is that you'll load in this data to plot this elevation profile, and then you want to use your diffusion model to see kind of what rate of uplift gives you a good match between the observed topographic profile and your model for hill slope diffusion. So I guess hopefully the picture over there looks something like this elevation profile here, and you want to try and get a match between those two, as within some reasonable range. So what you'll do is you'll change the rate of uplift. I give you the other parameters you need to use in the model, and you just want to change it until you get a good agreement in the general shape between this natural example and the model. So that's part 2. After that, you'll make a plot and put some stuff on there, some text. So that's that, and I hope that you find this to be a little bit more straightforward this week. There's no pandas, and so that should make things a little bit easier in some respects. But we'll see. We'll be here to answer questions and help out with things. And at this point, I guess, are there any questions about this exercise? Because I think if not, then you guys are free to get started. Like the other exercises, there's a section answers down here, and Yorina is just asking all the answers go in the answers section, not sort of hidden away somewhere in the inside. And I hope if that's been the case, you're welcome to maybe let Yorina know so that she knows individually where to look. But from now on, if you can, put the answers down there.